So with no further ado, we're going to move on to our presentation. David Crawley will be talking about the Ubiquity Robotics project, and he's going to bring Hercules here. He might need some help in hauling Hercules up onto the table.
He's going to leave Hercules where he is right now.
He's going to be left on the floor.
Left on the floor.
Okay. And are you wired up?
I'm wired up. Very good. Who's running? Who's running? All right, again. There you go. Good. So, I'm very humbled to have been asked to speak here tonight. And I really know that my humility is well placed because when Alan asked me to speak, he said, David, I'd really like you to speak at the Brew Robotics Club. We really don't have anyone else. So today, instead of talking about robotics, because you see, really, I personally don't know anything about robotics. Instead, I'm going to be talking about the Dark Ages. The Dark Ages were a period in history from about the fall of the Roman Empire, the 5th century AD, to about the 15th century AD. They were a period of economic and technical stagnation that was resulting in slow growth, poor social and economic conditions. And the Dark Ages were characterized by a couple of sort of mindsets. The first mindset is that dogma was priming, particularly the dogma of the church. The second thing was that knowledge comes from authority. There was this notion of a single true church that everyone had to obey. And if they didn't obey, well, there was something called an Inquisition that could take care of that. Faith and authority were kind of unquestionable. And there was this notion that we know the true way. There was this notion that we have an answer, that we understand and that we know. Obviously, the Dark Ages ended with the Age of Enlightenment. The Age of Enlightenment was characterized by the concept that experiments were priming, that knowledge comes from the real world, and that we should sort of think about multiple points of view. In the Age of Enlightenment, critical thinking became very important, and you had this notion that we must find the true way. We had this notion that we must accept our own ignorance. And of course, the Age of Enlightenment led to the scientific revolution and all of the sort of wonderful benefits that we are that epitomize Silicon Valley, that epitomize the wonderful things that we've got going on here. And really, when I think about the Age of Enlightenment is really characterized by greater learning. The fundamental difference between these two sets of attitudes is how quickly you learn. How quickly you learn. And the rate at which technology can advance. And so why on earth am I talking about this to a robotics club? I mean, what the hell is this about? Related? How does this relate to the Brew Robotics Club? So I'm going to ask you guys: how many of you guys have a robot at home? Everyone should have their hands up. Everyone should have their hands up. How many of you have a general purpose robot at home? Not like a vacuum cleaner, like a general purpose robot. Okay? 2, 3, 4. A few of you. How many of you have a general purpose robot at home that is working right now? Okay?
Good.
And how many of you have a general purpose robot at home that's common, that lots of other people have? None of us. And the reason why none of us have, even here in the Brew Robotics Club, none of us have Rosie at home, is because Rosie doesn't exist. Rosie doesn't exist. And the gap between, now how many of you would like Rosie to exist? I certainly would. You all would. You all would. And the gap between Rosie's existence and where we are today, that gap, that difference is in learning. The reason that Rosie doesn't exist today is because we don't know how to make Rosie yet. And so I've talked about the gap between, the Dark Ages and the Age of Enlightenment. This ethos, this thinking about learning and how to learn, that has continued to this day. And, I'm a lean practitioner for a long time, so I tend to use the lean lexicon. And it's characterized by several things. One is PDSA, Plan, Do, Study, Act. The sort of Gemba principle, the concept that you should really go to the real world, go to the real place, to study real things. This notion of multiple points of view, that's represented by what lean practitioners call set-based concurrent engineering, where you pursue multiple options at once until you figure out which one works the best. This notion of critical thinking is embodied in the concept of the obligation to dissent. Notice I don't call it the option to dissent, I say it's the obligation to dissent. And then the last thing is that we must systematically find the true way. We must systematically find it. And so I'm going to talk today about PDSA. There are these many principles that we could go into in a lot of detail. But today we're just going to touch briefly on this concept of PDSA. So what is PDSA? It's called Plan, Do, Study, Act. Deming, sometimes it's known as the Deming cycle. How many people here have heard of Deming? Yeah, most people have heard of Deming. Deming himself called it the universal sequence for breakthrough, which I think is a great description. Or he sometimes called it the Short cycle. In the military, I went to Sandhurst, which is sort of the British equivalent of West Point. They have something there called the OODA loop, Observe, Orient, Decide, Act. But my favorite really is just the scientific method, which we all know of from high school. The scientific method consists of hypothesis, experiment, results, conclusion. 4 phases. Hypothesis, where you try to figure out what it is you're trying to prove. Experiment, where you actually do some work to try to understand what the experiment is. Results, where you look at the results of your experiment. And conclusion, where you come to some kind of conclusion. And it's a systematic method of learning and problem solving. And insofar as we cover this, just to sort of emphasize that point, there are these 4 points: plan, do, study, act. Where you try to plan is where you try to write down your unknowns. Do is where you implement experiments, write code, build hardware. Study is where you test that code, you trial the hardware, you analyze the results. And act, where you try to document working systems, tell other people about it, bring systems in for a demo, or determine where to apply changes. There are these 4 distinct phases which require you to learn. Just one more quick example, and then I want to break into what some of the guys on our team are doing. Now, how would you use this to find the best restaurant? It's a universal method of learning. The first step would be to try to gather some potential options. The next step would be to visit some restaurants. The third step would be to make some notes about the qualities of each restaurant. And then the 4th one would be to standardize information. Just a quick example. So how do we implement this practically in the Ubiquity Robot project. The Ubiquity Robot project really started with this problem statement. Which is on the front page of our wiki, which is how could we create a low-cost robotics platform with meaningful capability to enable a broad range of applications? Because where we are is that current generic robots don't exist. Where we want to get to is a situation where you have generic robots that can be built for less than $500. So how can we build a robot with high endurance, payload vision, and navigation capabilities? So I set out 12 challenges or 12 tasks of Hercules, which is why it's called the Hercules Robot Project. And you'll notice that those 12 tasks, keep them here. We keep them in a location. And note that this location has 4 steps: plan, do, study, act. And the 12 challenges are all things that we're familiar with. Can we do basic motor control? That was one of the first challenges that we did that we've achieved in our robots moving around. Can we do face detection? That's something that Juno is going to be speaking about. There's a whole series of challenges around delivering pizza. There are challenges around moving well enough to be able to deliver pizza. We have challenges around recognizing people and being able to see them in a room. We have challenges around remaining localized for lengthy periods of time. Those all represent unknowns. And as our teams, and we have several teams in the Hercules Robot Project, as they succeed, we're going to move them into an investigational stage. Once they've coded or built the hardware that they need, then they start to test, and then in the end, they're going to document and conclude. And so we've broken the task, we've broken the task down into 5 different teams. One team deals with our computer infrastructure. One team deals with our navigation system. One team deals with our vision system. One team deals with our propulsion system, motors and so forth. And one team deals with our overall mechanical system. We've got some of the representatives tonight to tell us a little bit about how they are tackling the problem, what some of the problems that they're tackling are. And so we're going to go through some of them tonight. So Tuna has been working on vision. He successfully got the robot, which is down there, to do some basic vision functionality. And he's going to go first. Then we'll go on to navigation and propulsion. So Tuna.
So maybe we can, so if you look at the robot should follow David's face. It's turned on. So the robot has a Raspberry Pi. We use OpenCV to do face detection on the Raspberry Pi. And it communicates to an Arduino board which controls the motors. And currently, when it detects the face, it determines whether the face is on the left side or on the right side, and depending on, or on the center, and depending on where the face is, the robot will turn towards the face. We also have a face identification, which you cannot see currently, but I can also detect the identity of the person. So some of the issues we ran into with this is that face detection tends to be very slow, and the Raspberry Pi is not a very powerful processor. Currently we are not using the GPU, so that's one of the steps that we are planning to do. In order to speed it up a little bit, we tried to subsample which works with face detection, but then it causes a problem with face identification. So a technique that we are currently using is we are doing face detection at low resolution, and then once the faces are detected, we go to identification at high resolution. Another issue currently is that the controller is a bang-bang style controller. So we are working on replacing that with a more of a PID type controller, which will allow it to track the face more smoothly. We're working on projects that include creating a database of faces, and ultimately the robot should be able to follow a certain person once it has ID that specific person and not follow some other person. We also work on techniques to set general objects as well.
Thanks, Tuna. So good work. And then if Kenny, could you come and talk about mechanical? One of the things we're trying to do as we think about these sections is, can we try to professionalize a little bit some aspects of constructing the robot? And Kenny is taken on trying to do the mechanical sections of this, which is actually one of our biggest spend items. If we have a $500 target, mechanical is going to be one of the biggest ones. So Kenny is going to talk a little bit about some of the things that he's been doing to try to optimize our mechanical system.
Thank you. So my name's Kenny. I don't have a huge background in robotics, which actually benefits David's method of learning, because I don't come in with a lot of preconceived notions. What you see here on the floor is not anything we designed. This is the base of a electric wheelchair. And this was done as a test-bed platform to test out all the ideas that the software guys and vision guys and navigation guys are working on. And that's great, but it doesn't have a lot to do with the mechanical design of building a $500 robot. So what we're trying to do is, from a very low level, small mechanical team, is look at what is the best way to achieve a certain set of goals while still maintaining what is a pretty small price point for the goals. We think it's possible, but it's definitely a challenge. So what are our goals? Well, we want a robot that can navigate in human-built spaces. And how we've defined that generally is based on ADA guidelines. If any modern building is built to within those standards, so that you have outside doorways that are 36 inches wide and no narrower, inside doorways 32 inches wide, no narrower, certain ramp angles, certain obstructions in the floor. Those give us basic guidelines. If our robot can at least meet those, it should be able to function in an environment that's at least modern, like this building, for example. A competing goal is we want the robot to be large enough for meaningful interaction, complete meaningful tasks. We don't know what that is. We're trying to design a general purpose robot, which I can tell you all of the mechanical engineer background people at the meeting were pulling their hair out saying, what the heck are we supposed to do if we don't know what it is supposed to do? How do we design something when we don't know what the end uses are? Well, we basically decided we need to make the thing big enough to be stable enough to function with a number of different potential uses. Can it grab something off a table? Can it lift something, what's the max payload? We want to have something reasonable. Can it have an extension to have telepresence at a human height and not fall over or tip over? That all points to having something larger. However, we also want something that can navigate in human spaces, which means we want something smaller. These are conflicting goals, and the basic design is we're going to make it as large as we can without getting in the way and knocking into walls all the time. Through a couple iterations in trying to balance this stability and maneuverability based on building some prototypes out of plywood and casters and going around and trying to look at obstacles, we basically have gravitated towards a simple design using differential drive wheels in the front basic casters in the back. There's a whole lot of other ways. There are dozens and dozens of different ways to configure a robot. We were looking for something that was fairly simple and robust. And any errors introduced in navigation by casters, we just said, that's okay, the navigation team can handle it. So it's off our plate. So far, this is what we're looking at. Probably something that's about 18 inches wide, maybe 20 inches long in total, to give you a perspective. A little bit smaller than this example here. And we're hoping to provide, ideas for the future, maybe some sort of attachment mechanism that's universal, so that as a general purpose robot, you can have some good bolt holes to attach an arm to attach, I don't know, whatever it is people want to do with it. We want to make sure that there's attachment points, there's sensor mount points, that it's made for hobbyists to do what they want to do and not have a bunch of limitations built in from the beginning. So that's the overall mechanical design. We haven't gotten much further than conceptual drawings and plywood, but hopefully when we get into the internal structure and things like that and manufacturing, we'll have a lot more to talk about.
So one of the key problems that we've had is the computer system that we've been using, and I know that many of you are interested in whether or not we can get ROS to run on Raspberry Pi. We've been working on getting ROS Groovy to run on the Raspberry Pi. Kurt has been doing that, so he'll give us just a brief update of how he's getting on in terms of getting ROS Groovy to run on the Raspberry Pi. He's been having a lot of success through his persistence, diligence, and hard-headedness.
I guess for this month, I'm not going to have too much to report. I have been working on that. I guess Richard has put together Forte running on the Raspberry Pi. I've been focused on getting Groovy up and running on it. For desktop full, which is 179 packages, I've got 3 to go, all small. It was a little bit of a slog, mostly because we are not cross-compiling it yet. We haven't set that up. We thought we would brute force it on the Raspberry Pi. And some of these have taken a substantial amount of time. And I guess the other things that we've learned along the way, the Collada libraries took a bit of time. The OpenCV, doing OpenCV2 also was a substantial amount of processing time, but it wasn't too difficult to get beyond the glitches, which were all basically external dependency problems that we came across. There's one new group of packages that are in the Groovy set, which is the point cloud libraries, and the packages that run on the point cloud libraries. It too takes a while to do this without a cross compiler, a little more than 2 days on a Raspberry, and I'm cautiously optimistic. I've now gotten that to compile completely through, and it looks pretty clean. I have been lurking on a couple of these forums, a little bit nervous in that some of the issues that we came across were compiler parameters, where in the case of the point cloud libraries, you actually had to understand the architecture. So clearly they are doing some very low-level, highly efficient calls in their code, and the compiler options didn't find or understand or work in the Raspberry environment. And as such, a little later on in the compiles, there were certain attributes that the compiler actually needed that they expected to get from the architecture or the CPU that was being used. And when we actually told it was an 1176 Broadcom CPU, it wasn't able to figure out the Indianness of the processor, and we actually I'm sorry?
There's ball.
Well, we just wrote a real quick utility and said, okay, it's a little endian. and hard-coded that in and was able to get past that piece. And then there was also some internal subdependency errors in the point cloud libraries that we had to alter the catkin build to get it running. But we've actually got through all those things, and I'm cautiously optimistic that by Saturday I'm going to have this thing done, and we'll actually see if it works.
Okay, last of the 5 teams is Alan around. Alan has been working a little bit on trying to get our navigation stack in order, so that because I know that he wants to have the piece of the letters.
So, I mean, there are a couple of different sensors that have to be integrated for navigation to work. So, we haven't decided how we're going to actually do odometry yet. Right now, we do have ball effect sensors on the motors, so we can count motor rotations. That hasn't been decided if that's going to be the final way we're going to do odometry. I've been working with both the NITO XV11 LDS sensors and the Connects. Made a discovery saying today the Windows Connect version does not work with ROS. One guy in Germany got it to work, but no one else has been able to repeat that. So only the Xbox version. And the reason I know that is we go closer. Sorry, Mike. Thank you. Okay, so right now I'm waiting for a stable Raspberry Pi version, which looks like we're close to getting. I've been doing all my tests on Forte on Ubuntu, and one of the things we don't know yet, can a single Raspberry Pi running half the nodes be enough? How much of the autonomy is going to be on the robot? How much has to be somewhere else? That's something we have to decide. The other thing is, right now we are running the robot with a Wi-Fi dongle. Maybe that will put our own wireless router on there and save an extra USB port for the Raspberry Pi. That's where we are so far.
So I really want to thank the team, because they're the guys that have done all the work. I just have really one more question of everyone here. Does anybody know who this guy is? Anyone have any idea?
Napoleon?
No? Not Napoleon. John Radford?
Sir Francis Drake.
Got it. The first part is correct. He actually was knighted. Sir Francis is actually right. It's actually Sir Francis Bacon. Sir Francis Bacon. Does anybody know who Sir Francis Bacon is and why he is in any way important or relevant? He invented bacon and eggs. Good guess. Good guess. But no. What did he come up with?
He goes through a bunch of plays for this other guy.
He goes through it, but he actually was a polymath. He's known because he came up with the scientific method. He came up with the notion of hypothesis, experiment, results, conclusion. He came up with this method of learning. And so really, if I think about how are we going to make more progress in robotics, to me the sort of calling cry is let's try to figure out how we can learn faster. Right? Let's figure out how we can try to learn faster. And he gave us some ideas. There are more modern ideas that can help us. But I think if we can bring those ideas to learning about robotics, then we can get to where all of us want to be, which is, Rosie in our living rooms. All right? Any questions or for me? Yeah. Sure. So his question was, can I explain the whole $500 meetup group? Absolutely. Now, Every Saturday at 1:30, we meet in the Hacker Dojo, and we try to make progress on our challenges. We try to make progress really on trying to learn how to build a better robot. We have a problem statement. This is the problem statement. How can we create a low-cost robotics platform with meaningful capability to enable a broad range of applications? You know, which really comes down to how can we build a robot for less than $500. Anyone who wants to come to that robotics event, please come. If you have your own projects that you want to do, please come. Because my belief is that we can all make progress. We can all make progress faster if we all make progress together. None of us, I think, knows the answer. We've got some great roboticists in the room, but I certainly don't know the answer for how we can get there. But if we put ourselves in a mode of learning, we might get there a little bit faster than otherwise. So come on Saturday, 1:30. We meet then. We're often there on Sunday and on Monday and on Tuesday as well. But just come, and then we'll sign you up. Whichever area you're interested in, you can gravitate to that area. Wherever you can contribute, we're just happy to have people come and participate and hack with us. One of the reasons why I always said no to doing this talk was because, you know, actually I really want to hack and don't want to spend my time writing presentations, right? And to me, that's really kind of an important ethos that I hope the group can absorb, and I hope the group can get into a mode where we're doing PDSA cycles every week. And every week we set a new hypothesis for us to break through, and every week we try to learn more about that hypothesis. We're not there yet as a team, we're not there yet as a group. We are ever far from perfection, but you know, I hope that we can get there and learn faster. Any other questions?
I think my question is a little bit related to what you're talking about tonight. How much does the Google self-driving car cost?
So, the question was, how much does the Google self-driving car cost? I don't know what the answer is. Anyone from Google here who can elaborate on that?
I think the Velodyne sensor alone is about $35,000.
So, yeah, absolutely. $35,000 for just one of the sensors.
Just the sensor on it.
Just the sensor, right? $35,000. You know, I'm always amazed at how, you know, pushing for simplicity leads to actually better engineering answers, right? Pushing for simplicity leads to better engineering answers. Any other questions?
What about the stairs?
What about stairs? Great question. What we've said so far is anywhere that's ADA compliant, right? And ADA compliance implies a 1 in 12 ramp with a very small step, about a quarter of an inch. We're probably going to over-design to that ADA compliance a little bit to make the navigation team's job a little bit easier. But you know, that's been our guiding principle so far. The other guiding principle is, of course, well, what do we really see in the environment? You know, I'm sort of always amazed. You know, I talk about this sort of this Dark Ages period, and in the Dark Ages there was a case where there were 3 men sitting in an inn, and the question was, how many teeth does a horse have outside? And they chose to sit there and talk about how many teeth this horse had, and they would make reference to Aristotle and Plato and all of these established references. But the reality was that a young man who was sitting there at the time said, well, there's a horse outside, why don't we go and take a look? And it seems almost that the same thing sometimes happens in the robot group. I was sitting in a group, in the robot group, and I was sitting there and said, well, what size stair should we make it? Should we make the robot able to come over? What kind of bump should we design for? And everyone's immediately jumped in and said, well, you know, ADA compliance standard is this, and you know, I've seen stairs that have that, and so on and so on and so forth. And I said to the group, well, let's get up, walk outside with a tape measure, and see what we can see. What do we actually observe in the real environment? And that's what we should be guided by. And so this whole thing is a giant experiment. I don't know where it's going to go. But if at the end of the day we have a robot that can move around an environment that we all tend to occupy, that's great. If we design to ADA compliance, which is what we put here, and then the robot isn't useful, we failed. Right? Any other questions? So for all of you, please do come to the Saturday event. It's 1:30 at the Hacker Dojo. Anyone is welcome. Anyone can show up, contribute in any way that you see fit. And I'd love to see some of you come to that event this Saturday or any future Saturday. Question? Yeah.
Can you expand even more broadly on what Hacker Dojo is?
Sure. So Hacker Dojo is a hacker space. It's in 599 Fairchild. It's a former Google complex. It's just down the road from here. If you're a member, I think membership costs about $100 a month. I'm a member, but you don't have to be a member to come to any of the events that we hold. It's just an open hacker space. It's open 24 hours a day. Members can book events. I book an event every Saturday for robot hacking. And we have various bits of kit. Some of it's been donated. Some of it has been given. Quite a lot of it I paid for out of my own pocket. And you know, that's all there for people to use. And people can come. We have little project boxes. People can come and do a little project for us. The goal is that all the projects can be done in a day. We're not there yet, but that's the idea. And we have people doing simple things. We have people doing very sophisticated things. And obviously we want more people doing more interesting problem solving. Yeah, Alan? So yeah, his question was explain about the value of learning from mistakes. Now, I think it's very important that we all learn from mistakes. And because I think it is so important that we learn from our mistakes, we've instituted what's called the Blue Smoke Award winners. By the way, I'm way ahead in this. Anytime that anyone blows anything up, burns anything out, or sets fire to anything, crashes anything, any sort of, you know, real copper bottom error, it goes into our Blue Smoke Award winners. And as always, trying to be reflective, we put it in the humor section. You can see that you know, we have a couple of the top mistakes here. And it's very important that we do the cause and we figure out what the learning was. And that we publish it on our website and everyone can see and talk about it. Because if we don't have mistakes, we're probably not having any learning, because frankly, if we knew what we were doing, then we wouldn't be making any progress, right? So yeah. If we knew what we were doing, it wouldn't be research. All right.
Thank you very much. A number of us old-timers have, over the years, talked about how neat it would be if there would be a place that we could go to hack on robots. And we always came to the conclusion like, well, geez, we'll never be able to afford any space. It's really expensive here. And that's basically what's happened here with Hacker Dojo and the Saturday stuff. I was there last Saturday teaching the class on the robot here, but there were like 15 people just trying to figure out robots over there. So it's a good place to go. Give it a try, and it's every week. So come on down. Okay. So, thank you very much. Okay, and we'll see some progress as time moves forward. And with that, we're going to wrap this meeting up and go into random access, which means we just all talk to one another. And thank you very much, and we hope to see you next week. No, next month. Sorry. Thank you.